lecture we are talking about partitioning. Now, as the next logical step in the backend design process, today we will be talking about a process called floor planning. So, first let us try to understand what floor planning really means. Talking about the problem definition, so what floor planning constitutes is that as an input it will take a set of blocks. Now, the blocks may be fixed at this stage or it may also be flexible. So, actually what we mean by fixed and flexible are as follows. See, some of the block may be pre-designed, means we know the exact dimensions of the block in terms of the width and the height, but there may be some of the blocks we know how many components are inside that block, but we have not fixed up the shape of the block as yet. Okay. So, such blocks we call as flexible blocks. So, as an input to the partitioning problem, we have a set of blocks which can be both fixed and flexible. Now, each block to start with will be assigned a width and a height value which will give an area. Now, in case of fixed blocks, this Wi and Hi are statically fixed, but in case of flexible blocks you have to keep this area fixed. You can adjust the values of Wi and Hi according to your requirement. So, rigid and flexible, whatever I am talking about, these are the constraints on the shape of the block. So, a block may be like this, thin and long, it can be a square and so on. Well, so we have specification regarding the blocks, and for blocks which are of fixed shape, we also would be having some information about the exact location of the signal pins. But the blocks which are flexible means the blocks have not yet been designed fully. So, the positions of the pins are also flexible there. So, if the blocks are fixed, we also have some pin locations, this may be required, and of course, a net list which will indicate the interconnection among the blocks, how they are interconnected. These are the inputs to the problem of floor planning. So, what we require here is that we want to find a tentative location of each block on the floor plan, on the floor. Given a rectangle which indicates the area of the chip, say, on which we want to lay out the blocks. So, we want to find out the tentative location of the block. Suppose block A will go here, block B will go here, block C will go here, and so on. These are the rough locations of the blocks. We are not showing any separation between the blocks through which the interconnections or interconnecting lines will go through, but we are roughly trying to get a relative ordering or placement of the blocks. Okay. And also, as part of the flexible as part of the floor planning, if there are some flexible blocks, so at the end of the process we will also get the shapes of the flexible blocks. Suppose D was flexible, but when you place it finally, we will say that, well, D will have to have a shape like this. And of course, objectives can be many, we will be just look into objectives again, but typically the objectives are to minimize area, the total area of the floor plan, and of course, to reduce the wire length for critical nets in order to minimize the delay. Okay. So, let us take a simple example for fixed blocks and see that well, means how a floor plan really looks like. So, here we have taken a very simple example with 5 modules A, B, C, D, E, and in terms of some unit, the width and height of the blocks are also given. So, as you can see that the blocks A and C are the smallest, each of width 1 and height 1. D has width of 1 and height of 2, E has a width of 2 and height of 1. So, D looks like this and E looks like this. This is your D, this is your E. but one thing you observe, if we rotate the block, D and E will look the same. So, as part of floor planning, sometimes we also have flexibility in orienting a block suitably by rotating it, or even you can take mirror image of a block. Of course, B is the biggest one, width 1 and height 3. So, for this particular problem, this diagram shows some of the feasible floor plan. There can be many others, but I am showing only 3. So, the first one you see, B has a width of 1, height of 3, B is positioned like that. E has a width of 2 and height of 1, it has been positioned like that. D has been rotated, width of 1 and height of 2, D has been rotated, and A and C have been put side by side out here, they are one by one. This is another alternative, D has been put in the middle, AC here. This is another alternative where B has been put in top in a rotated fashion, D comes here, E is rotated here, and A and C out here. So, as you can see, for a given set of blocks, there can be large number of such you can say such feasible floor plans. So, in order to find out which one is the best, we will have to evaluate some kind of a cost function on each of these and find out that which gives us the best solution. Okay. So, here we will be looking at the way we can estimate the cost of a given floor plan. But before that, let us look at some of the design style specific issues, because this is important in understanding the impact of floor planning when we are trying to design something. It can be a full custom design, it can be standard cell based, or it can be gate array or FPGA based. Now, the point to note is that for a full custom design, well, we have complete flexibility in the placement and the shapes of the block. So, the floor planning problem, as we have just stated, that applies completely to full custom designs. Blocks may be fixed, blocks may be flexible, they may be placed anywhere. So, you have a general description of the blocks and we can place them in any suitable way in order to optimize or minimize some cost function. But in case of standard cell, you recall, here cells are always picked up from a library. So, it is not that we have flexible cells. So, all cells are fixed or rigid, which means the dimensions of the cells are fixed, so also are the location of the pins. So, here we do not have any flexibility in that. And moreover, if you recall the standard cell style of design, here these cells are placed along rows on the surface of the chip. So, the floor planning problem and the placement problem becomes the same here, because the placement problem means it is a refinement of floor planning, and to find out the exact location of the block on the chip along with its exact dimension. So, actually in a placement you also keep some space for routing interconnection. So, in a standard cell design, floor planning and placement does not make any difference, because when you say I am doing a floor planning, well, these rows are already defined, you have to plan, that means where do you want to place a cell, on means in which row, in which position. So, that also gives the placement, right. But if your netlist is large, normally we follow two steps here. First is that globally we do some partitioning so as to divide the big problem into several smaller sub problems, and each of the sub problems we try to route or place in one or few neighboring rows. Okay. And the problem is quite similar for gate arrays or FPGAs. There also the location of the devices are fixed on the chip. So, basically we have to map some block of our design of our netlist into some particular cell of the array, defined gate array. So, there also floor planning and placement becomes the same, right. So, this is something you have to keep in mind. So, that whatever algorithms we discuss here for floor planning, they primarily would apply to full custom designs. For standard cell and gate array, we do not need this type of floor planning really. Straight away you can go for this type of for the step of placement finally. Okay. Before talking about the ways floor plans are represented and the different algorithms for generating floor plan, first let us look at again in slightly more detail how to estimate the cost. Now, with regards to the cost, the first thing to note is that we have taken a very simple example and showed 3 possible solutions for it, but for a typical floor planning problem with typically large number of blocks, the number of feasible solutions can be very large, and in general finding the best solution out of that, you cannot have anything better than exhaustive search. You will have to evaluate all possible and find, and you will see later I will just show a few small representative examples that as the number of blocks n increases, the number of feasible solution increases exponentially with that. So, as a result the problem becomes an NP hard problem. So, we typically look at some kind of a heuristic in order to get a good solution instead of exploring all possibilities and trying to find out the best. Okay. And in fact, we talked about area and interconnection, but there are several criteria which are used to evaluate the quality of a floor plan. Of course, the most important are to minimize the total area. Say I have a rectangular region, I will be creating a floor plan. So, I will have to find out what is the total width and what is the total height of this rectangular bounding box I require, that is the estimate of the total area. Similarly, I will have to estimate the total length of the wire and try to minimize that, because yes.
So, in the minimize area step, like we are given a chip and we have to place the blocks in that.
See, in this type of floor planning, the chip is a little far off. We are not thinking of a chip, we are thinking of a rectangular area. So, we are trying to think, that means what is the smallest such rectangular area in which you can map our entire design into, okay, because the exact chip layout will come a little later during placement. Okay. And minimize total length of wire is obvious, because it is natural to put those 2 blocks closer together which are strongly interconnected, and of course, the critical nets also should be taken care of. Maximize routability is important for certain design styles. See, for FPGA or gate array, maybe you will be able to find out a placement, because there are available cells on your chip, you can map one sub circuit into one cell like that. But when it comes to routing, say for example, in an FPGA, the total amount of routing resource is limited. The number of routing rows and columns in the chip, they are fixed. So, every possible placement may not be routable. You will find that there is a conflict, you are not able to finish the interconnection. So, in that case you may have to iterate, you may have to change the placement or floor plan, and again you have to try out the routing. So, one of the objective is to also look at routability. Of course, this we will discuss when we discuss the problem of routing later. And talking about the critical paths, because the critical paths will determine the delays. So, if we know the critical paths, we may also try to minimize them, and of course, we can have any combination of above, so area, delay, or area and the length of wire taken together. Fine. Now, this area and the total length of wire, these are the 2 measures which are most popularly used. So, the first question arises that how can we estimate the area? See, area is not difficult to estimate, because on the floor plan, the size of each of the blocks we are placing are known in terms of its width and height, or its total area, say AI. AI is the area of this block. So, since you have the area of each block known in terms of its width and height, and you are placing them in certain way, suppose you are placing them in this way, AI, BI and CI. So, you know the total width of the floor plan. Similarly, you can find out the total height of the floor plan. So, multiplying them, you can estimate the total area. So, once we have a floor plan, estimating area is easy, because the width and height of each of the blocks as we place them on the floor, they are fixed. Fine. Now, the second question is that how to determine wire length, because here, well, wires, yes.
This does not include the place, I mean, you look for the routing.
Well, here when we estimate the area, we are well, just like when you are building a house, you just say that these are the 4 rooms and the adjacency. You do not keep any space for corridors at this level. They will get refined in the later phase. So, now we just say that this is the roughly the area of a block, this is roughly the area of another block. Since they are strongly connected, we place them side by side, but we do not explicitly keep space for routing here. That will get refined in the next step in the placement phase. Yes, fine. And at this step, since we have a very approximate layout of the blocks, so while determining wire length, we adapt a very coarse measure. Say the coarse measure is like this. Suppose on the floor there are 2 blocks. Say this is block BI and this is block BJ. Now, each of these blocks can be having several interconnecting pins or signal points. Okay. This may be also having several. Now, the way distance is estimated is like this, that here for the sake of estimating the distance of interconnection with respect to floor planning, we assume that each rectangle, well, you can define the center of the rectangle. So, we assume that all these pins are located in the center. Similarly, here you define the center of the rectangle. So, all these pins are assumed to be residing in the center of the respective block, and you compute the Manhattan distance between the 2 blocks, 2 centers of the blocks. Suppose a wire, a pin here was required to be connected to a pin here, but at this level the estimate would be just the distance between the centers. This is the estimate of the length of the wire, because right now we do not know anything about the routing regions or the channels. So, we cannot exactly estimate the wire length. So, we have a very coarse estimation. We just take the Manhattan distance and we estimate it. So, as is mentioned here, so all IO pins are merged and assumed to reside at the center of the blocks. And the overall wiring length is the sum of, well, this factor for each net. Cij is the connectivity between blocks I and j, that number of wires that connect I with j, and Dij is the Manhattan distance between block I and block j. So, you find out the sum for all possible pairs of blocks I and j, and you get an estimate of the total wire length. So, an estimate like this is normally used to find out the total wire length estimate. Yes.
So for all the blocks this is done, like there are some blocks in the, like it, for all the blocks we like calculate the factor and do it.
Yeah, for all pairs of blocks we do this, because I and j refer to 2 different blocks, Bi and Bj. So, there if there are n number of blocks, there will be n into n minus 1 such pair, n into n minus 1 by 2 in fact. So, here we estimate this for every pair of blocks, and then you find the sum total. Okay. As I told you, this area and the wire length are the most important measures to find out the area. So, to find out the cost. So, typically we estimate the cost as some weighted average of this area and this length. W and W2 can be user specified parameters, means onto which you are giving more emphasis on. So, you can estimate it. Of course, in addition you can keep some other criteria like critical net, because critical nets and delays, they are typically handled on a case by case basis. There is no general algorithm we can also take care of that, and it means optimize that in the same framework. So, you find a floor plan, and then you evaluate the cost of the critical paths, how are they crossing, how far they are, and then you try to make some perturbation so that the critical paths get improved. Okay. So, fine. So, before going into the algorithms, we talk about some of the data structures that we typically use to represent a floor plan. Now, one such data structure is called a slicing tree, which is based on the so called slicing structure. See, slice, as the name implies, well, I have something, I just cut it into two pieces, that is a slice, and a slice I can make either horizontally or I can make vertically. So, a slice divides an existing rectangle into two different rectangles. So, a given big floor plan, I can apply a number of such vertical and horizontal slices as I need, and I can get several smaller rectangles. So, the slicing structure can be defined like a rectangular dissection that can be obtained by repeatedly splitting rectangles using horizontal and vertical cut lines. And as a result we get smaller rectangles. Now, the order in which we are applying the cuts, that is captured or represented in a so called slicing tree. Now, a slicing tree is a binary tree. This models this slicing structure, means the order in which we are carrying out the slices. So, you start with the root of the tree, as you go down towards the leaves you get the details of the slices. Now, in this tree, other than the leaf nodes indicate blocks. Each leaf is a block. Block means the smaller rectangles which you get finally, but each of the other nodes, they represent a cut. It is either a vertical cut line represented by V or a horizontal cut line represented by H. So, if it is a purely sliceable structure where you can get each of the basic blocks at the low level by horizontal and vertical slices, then you can have a tree with V and H nodes only. But we will see subsequently that some of the floor plans may not be sliceable using horizontal and vertical cuts alone. These are called non-sliceable floor plans, and in those kind of floor plans we may introduce another third kind of a node called a wheel. Now, this wheel we will be discussing a little later, but for the time being we look at only V and H nodes using vertical and horizontal cuts. So, we show here an example of a slicing floor plan and the corresponding tree, the slicing tree. Just have a look at this floor plan and just have a look at this tree. Starting from the root, this V, this indicates a slice corresponding to this vertical cut, because you see this V partitions the tree into two parts, one comprises of F, G, H and I, another comprises of A, B, C, D, E, this part. Now, you have divided up into two parts. Now, in each of the two parts you just make a horizontal slice each. So, in this half, this horizontal slice will divide it up into F, G and H, I. So, it corresponds to this. Similarly, in the other one it divides into D, E and the rest. So, in the other part it corresponds to this. So, this process will continue. In the next level there is another vertical cut F, G, this, here H, I, this, and you get finally the blocks F, G, H and I. And on the other side you have another vertical cut D, E, this, you get D and E, and you have another vertical cut here where on one side you get the block A and the other side you get another composite block where you need another horizontal cut like this to get B and C. So, here once you have this tree, just if you traverse the tree from the root towards the leaf or from the leaf towards the root, means whichever way you traverse, you will get an idea regarding the order in which you are basically partitioning the total floor area into the floor plan, into the placement of the blocks. Fine. Now, one thing to note is that given a floor plan, the order you can apply the slices to arrive at this may not be unique. So, I am showing here an example to illustrate the non-uniqueness of the slicing tree. Take this example. So, here one possible slicing tree is this. So, the first vertical cut you apply like this. In both these examples, the first vertical cut is this. But here you start at the next level for this portion with a cut this. You divide it up into G and the rest here. But in this case, you start with this cut first, CD and the rest. So means in any sub block, if there are several horizontal or several vertical parts, you can apply them in any order. So as you can see that there are two alternatives. One is that you first cut G, then you cut this in the middle, then vertical cut CD and EF. Similarly here, you first cut this, then CD you can do using a vertical cut, then you apply a horizontal cut here, then a vertical cut here in the middle. So for the same floor plan, you can have more than one slicing trees. Okay. But we have said that all floor plans you cannot represent by simple vertical and horizontal cuts. Okay. There is only one primitive such floor plan layout which cannot be represented by horizontal and vertical cuts, and that is called a wheel. It looks like this. This is the only kind of a primitive floor plan structure which cannot be represented by simple slices. See, if you have this floor plan, you cannot apply simple horizontal and vertical slices, cut them and get them, because if you want to cut this, your block C also gets cut in the middle, that you do not want. So, this kind of a thing you call a wheel, and in the order in which we just name the blocks is that A, B, C, D and the middle one E. Now, it is possible that you have a composite higher level floor plan in which there may be some portions which may look like a wheel, and inside a wheel these A, B, C, D may be composite blocks themselves. So, in that sense you can have some kind of a hierarchical floor plan. Well, whenever you define the slicing tree kind of a thing, for example, if we again look back at the diagrams before. So, here whenever you have a hierarchical structure like this or a hierarchical set of slices you apply, well, you represent them as a tree. Now, this tree in some sense represents a hierarchy, like as if CD and EF can be combined together, and whatever you get, you can combine there by a horizontal line, you can put them together. So, again putting this and G horizontally, you can make a bigger block, putting this and this vertically, you can put a bigger block. So, this is some kind of hierarchy you are specifying. So, now let us look at an example which also involves this wheel structure, right. So, let us take a slightly complex example like this. So, this you can see that this block apparently looks quite complex, there are so many blocks, but if you look into it slightly in detail, you will find that there are several regions in this. I am trying to highlight this region. This is one region, this is another region, this is another region, and this is another region. Of course, whatever remains in the middle, this is another region. Now, just looking at the regions, you can observe that this is nothing but a wheel. If you call these regions as A, B, C, D and E, this is nothing but a wheel. So, at the top level, this has a wheel structure. So, now if we want to construct the so called tree that well, you can say analog of that slicing tree, because this is not sliceable, there will be some wheel nodes as well. So, here the tree will look like this. At the top level you have a wheel, we represent it by a node W. There will be 5 successors. The first successor, this one we are calling A, just if you recall the previous diagram, this we are calling A. So, let us start with this C and F. So, here they are divided by a horizontal cut. So, there will be a horizontal H node with C and F. Similarly, next one, this is the next one coming E and D with a vertical cut. So, this is a V node, E and D. The third one is this I and J with a vertical cut. This one is again a wheel. So, here you will get another W node. So, there will be 5 successors A, G, H, K, L. And finally, the middle one is B. So, for this floor plan you can construct a tree like this, where you can see instead of V and H you have a third kind of a node W. So, in general your floor plan can also contain wheel nodes, right. Fine. So, these are the ways you represent a floor plan. So, now we look at some of the algorithms that people actually have talked about, have used to generate a floor plan from a given problem, description of the blocks. So, in fact, there are a number of you can say classes of algorithms which have been reported. So, some of them I am showing here. Well, integer programming based approach is an interesting approach, well, which is of course based on a sound mathematical basis. Rectangular dual graph approach is another interesting approach, which is based on some graph theoretic concepts. And hierarchical tree based and simulated annealing, these are practical methods which are found to work better. And you can have other variations like some combination of these, or you can have genetic algorithm, etc. So, we will not be talking about the other algorithms. So, we will be just looking at the first 4. So, we start with integer programming based approach. Well, here what is done is that the floor planning problem is framed as an integer linear programming problem. So, we just show you with a specific problem that how this problem formulation can be carried out. So, let us just have a look at this. So, the integer linear programming formulation here is essentially what you do, given the details of the blocks, we try to model the problem as a set of linear equations which uses variables which can take on the values of 0 and 1. So, this is a 0-1 integer linear programming problem. Of course, there are some variables which are not 0-1, which can be arbitrary integers, we will see, but there are some variables which can take on only 0 and 1 binary variables. So, as the input we have description of a set of n blocks which we need to place on the floor plan, on the floor. These blocks we call B1, B2 to Bn. And in order to illustrate the formulation we will be showing, we are assuming that these blocks are rigid. Of course, there exists formulation where the blocks can also be flexible, but here we are assuming the blocks are rigid and also have fixed orientation. That means we cannot rotate the block. Well, again in some other formulation the rotation is also allowed, but here we assume that the blocks are rigid and you cannot rotate the blocks. And with each block we associate some information. Well, suppose this is the floor, the overall rectangle. So, the lower left corner we assume is having a coordinate 0, 0, this is the origin. So, with respect to the origin, whenever you place a block somewhere, this lower left coordinate is assumed to have a coordinate of xi and yi. So, xi yi is the coordinate of the lower left corner, wi is the width and hi is the height. Now, since the blocks are flexible, what we assume is that wi and hi are constants, xi and yi are values we have to find out, right. Okay. So, now let us see that how we can formulate this problem as a set of linear equations. So, just remember, for each block we have xi yi, the lower left coordinate, width and the height. Fine. So, what we require is that the main criteria is that given two blocks, say bi and bj, blocks bi and bj must not overlap. This is the main condition to be satisfied. Whatever floor plan we get, if we can ensure that no two blocks overlap, then we have a feasible floor plan. Okay. So, in order to have this, let us see that what are the inequalities that need to be satisfied. So, in terms of the sizes of the blocks, we have the sizes of I and j and also the coordinates xi yi and xj yj. So, the equations will be like this: xi plus wi less than equal to xj. I am writing 4 equations, then I am explaining which represents what. Yi plus hi less than equal to yj, xi minus wj greater than equal to xj, yi minus hj greater than equal to yj. Okay. So, I have two blocks bi, bj, where the lower left coordinates are xi yi and xj yj. wi hi are the widths and height, of course. This is wi, this is hi, this is wj and this is hj. Okay. Now, let us try to interpret these 4 equations. The first one says xi plus wi is less than equal to xj, which means block j is starting somewhere to the right of I. So, this essentially means that bj is on, or you can say bi is on the left of bj, because this xi coordinate plus its width, this is less than equal to the starting point of bj. So, bj is somewhere on the right. So, bi is lying to the left of bj. Similarly, in terms of y, if yi plus hi less than equal to yj, that means bj is on above bi. So, bi is, you can say, below bj. Similarly, this means if you take wj on the right hand side, it means xj plus wj is less than equal to xi. That means you interchange I and j, it happens this. So, this means I is on the right of j. So, bi is on the right of bj. Similarly, this I is below j, or sorry, bi is above j, bi is above bj, because hj plus yj is less than equal to yi. So, you see, just in terms of the relative positioning of these 4 blocks, in order to avoid them from overlapping, we have written 4 equations. And in order to ensure that the blocks do not overlap, we need not satisfy all these equations. If you look at them a little carefully, it is sufficient if at least one of these equations are satisfied. Okay. So, what you want is that at least one of the above equations must be satisfied. So, the way we express or we write down the equations should also capture this, that at least one of these must be satisfied. So, in order to do this, what we do is that we introduce for block pairs I and j, we introduce two 0 1 integer variables. We call them xij and yij. Now, the interpretation of the values of xij and yij are very simple. See, xij and yij, since they are 0 1 variables, they can be either 0 0 or 0 1 or 1 0 or 1 1. Now, these are the four equations which are given. Okay. The first equation corresponds to this 0 0 combination, second equation corresponds to 0 1, this is 1 0, this is 1 1. So, the combination of the xi yj values indicate that which of these four equations we are referring to, and depending on which equation we are trying to satisfy, the value of xij and yij will be that. The idea is that somehow we will show how we would be writing down some equations which will be combining xij yij with these. They will be composite equations, and we will also try to find out some value of xij yij which can be one of these four, such that this equation is satisfied. We will see, suppose that for certain particular value of xij yij, suppose it is 0 1. 0 1 means we are just referring to the second equation. So, the way we would be modifying the equation is that we will see that the other three equations will be trivially satisfied. Only this equation will act as the constraint which needs to be satisfied. So, we will have to suitably choose the value of yi and yj, for example, but others are trivially satisfied. So, there is no question of determining values of xij or yij, xi or yi. So, we will see this. So, we combine this with these two new variables to get some set of new equations. But before that, we also assume one thing. Suppose this is your floor plan you want to get, and there are some restrictions you are also imposing. What kind of restrictions? You are saying that the total width of the floor plan must be less than or equal to capital W, and total height must be less than or equal to capital H. Now, W and H may be specified by the user, or you can have a rough estimate as follows: W will be the sum of all Wi's and H will be the sum of all HI's. This will give you the trivial maximum values of H and Y, I mean the all blocks placed one after the other. Okay. So, there are some other obvious constraints which come up. These are, for any two blocks xi and xj, so the difference between their x coordinates will never exceed W, because this is the maximum. Similarly, the difference between their y coordinates will never exceed H. Okay, fine. So, now let us try to modify the earlier four equations, these four, taking into account xij and yij. So, I am showing you the modified equations. Xi, the first equation becomes, so earlier it was only xj, right, but now we are adding something to it, plus capital W xyij. So, I am explaining what this means. Second equation was yi plus hi less than equal to yj only, but now we are adding something more, h into 1 plus xij minus yij. The third one, xi minus wj greater than equal to xj minus w 1 minus xij plus yij. Similarly, the last one, yi minus hj greater than equal to yj minus h 2 minus xij minus yij. Well, now let us look at this equation a little more carefully and find out what this means. So, I just told you that the xij yij combination actually tells us that which of these four constraints are in force, you can say, which is the one you are checking, and the combinations were 0 0 0 1 1 0 and 1 1. Suppose the values are 0 0, then you see the first equation is same as the original unconstrained equation, xi plus wi less than equal to xj, this part is 0. But the other equations you note, for the second one, yi plus hi less than equal to yj plus h, this will always be true because h is the maximum height, okay. This will be trivially true. Similarly, xi minus wj greater than equal to xj minus w total width, or put it the other way around, xj plus yj plus wj less than equal to xi minus w, xi plus w, this will also be trivially true. Similarly, this one, yi minus hj greater than equal to yj minus 2h. So, other three equations are getting trivially satisfied. So, only one of this equation is having the hard constraint, that has to be satisfied by suitably selecting the values of xi and ya, xi and xj. Similarly, let us take another combination, suppose the values are 1 and 0. So, for 1 and 0, only for the third equation this portion is becoming 0, this part is disappearing, but for the other equations you see they are getting trivially satisfied. The first equation is becoming xj plus w, this is becoming yj plus 2h, this is becoming yj minus h, they are getting trivially satisfied. So, only one of this equation is having this new term as 0 and the other terms as either w or 2w or h or 2h. So, they will be trivially satisfied there. So, this is the way in which the constraints are modified in order to take care of well, the fact that one of them need to be satisfied. So, now if you pose it as a problem with so many variables, so now you are required to find out xi, xj, yi, yj, xij and yij. So, you will come up with a combination which will also give you some values of xij and yij. So, actually which will tell you some orientation, xi bi is on the right of bj or bi is above bj. So, for that what are the values of the other things, so that all of them get satisfied. So, now with this we can formulate the linear programming formulation now. So, it is an integer linear program ILP, since all the variables have integer values. So, in the ILP formulation, the way we are presenting here is that, well, instead of assuming variability in both the directions, we are assuming that width is w, but height we are trying to optimize, minimize. So, let us call it y. Well, of course, height is less than equal to h, this h remains, but the actual value of y or of the height is y. So, now our formulation becomes like this. Minimize y, this is we want to do, subject to, there are several constraints. The first one are the obvious constraints, xi plus wi less than equal to capital W, yi plus hi less than equal to capital Y. Then there are the 4 constraints we had just shown, these 4 equations. Okay. These 4 equations. So, these 4 equations will come in here. Then some trivial constraints that xi and yi must not be negative, xi greater than equal to 0, yi greater than equal to 0. So, this is the integer linear programming formulation. So, of course, the first equation is for all I, second one is also for all I, the last ones are also for all I, but the middle ones are for all pairs of values of I and j. So, if you roughly estimate, that means how many equations and variables you are trying to solve. Well, in terms of general integer variables, they are xi's and yi's. There are 2n such variables. So, integer variables are 2n, and 0 1 variables, how many are there? Those are the xij and yij. So, xij for every pair you will be having. So, the n into n minus 1 in general, n into n minus 1. And how many such equations or constraints you are having? Total number of constraints. This also you can estimate. For the first one corresponds to n for all I. This is n, this is n, and this is again n, 4n, 4n plus. Here there are 4 equations. So, you again have a look at those equations. There are 4 equations with combination of values of I and j. So, there are 4 equations with n into n minus 1. So, this is roughly the number of constraints which are there, but actually we need not have to take care of bi, bj or bj, bi. So, you can have it divided by 2 also, that way you can specify. So, that it becomes half, but still you can see that the number of constraints is of the order of n square. So, the problem is that if the number of blocks are large, then this method is not feasible. Well, this method is mathematically very sound. If you can formulate it, you can feed it to a ILP program, it will find out a solution. But the problem is that it will take enormous amount of time for big problems. So, actually what people normally do, so instead of feeding the original floor planning problem to ILP and trying to solve it, it first does some kind of a divide and conquer. It partitions it into sub problems and then feeds each of the sub problems to the ILP solver. Okay, fine. And as I had said earlier, that ILP formulations for the other variations also exist, but I am not going to detail. Number one thing is that, well, you can also take care of orientations of the blocks, that whether, means if you are rotating a block by 90 degree or not. See, rotating is not very difficult to capture. For each block you can add another variable, say Ri, which indicates whether it is rotated or not rotated. It will be 0 1 variable. And if it is rotated, then the xi and yi, or means their hi and wi gets interchanged. So, the equations you can accordingly modify. Now, another modification was suggested, that was for the flexible blocks. Flexible block says that you have wi and hi for each block, which gives you the area. Now, they are keeping the area fixed, you try to find out the actual values of Wi and Hi. But the problem here is that if you put the constraint as it is like this, Ai equal to Wi Hi, then it becomes a non-linear problem. But there are ways to convert this non-linear problem into a linear problem and then use it for ILP solution. So all these things are there. Now in the next class we will be looking at some other methods using which this problem of floor planning have been tackled by different researchers. So thank you.